Okay, good afternoon, ladies and gentlemen. It's my pleasure to welcome you all of today's event. My name is Yingche Xie Ali, and I will be your host today. First, let's welcome the president of National Tsinghua University, President Gao, to give the opening remark. Let's welcome President Gao.
Thank you, Ali. Good afternoon, everybody. Welcome. And Professor Chu, welcome to the National Tsinghua University. When we talk about energy, usually we talk about things in big numbers, gigawatts, terawatts, terajoules. It's really hard to put that into context. So let me put things in some proper perspective. Everybody raise your hand if you know what ChatGPT is. I'm pretty sure that's everybody. You know, the energy required to run ChatGPT every year requires enough energy to power Kaohsiung, the city, which is the second largest city in Taiwan, 5 years. So every time we use ChatGPT, over a year's time, that's enough energy to run a whole city for 5 years. So that's a lot of energy. And not only that, every time we ask ChatGPT a question, it required a bottle of water to cool the system. Okay, so when you think about the advanced, everybody talks about AI these days. If you think about how this technology will change our lives, of course, it can help us have a better life, but at the same time, it put a tremendous demand on our energy grid. And that's only ChatGPT. As we know, there's Gemini that came online and other platforms as well. So energy is a very important topic, an important challenge for all of us to tackle. And the National Tsinghua University, we're doing our parts. So we are the only university, and the first and the only, to have a nuclear science faculty, college. And we're the only university with our own nuclear reactor on campus. So we've been training these talents, nuclear engineers, over decades. And I think going forward, the world will need more and more of these talents, whether it's traditional energy for energy, or the new small modular reactor, or the use of nuclear science in medicine, in space exploration, and in many, many other fields. So NTHU, we're doing our part. And as we know, energy is also a very important geopolitical topic. Today's event is organized by our Taipei School of Economics and Political Science, because that energy is more than just science and technology. It's also geopolitics. It's also about commerce. And we know that last month, the UN COP29 was a meeting where in the very first day, more than 200 countries and regions come together and achieve a consensus of working towards an international carbon trade platform. And that will have a tremendous impact on industry, both locally in Taiwan, as well as around the world. Large companies, small, medium-sized enterprises will face a new reality of carbon trade, working towards net zero. So, and what we're doing at NTHU is we also established a College of Sustainability. Our first new dean is sitting right in front of us, Professor Dai. This new college will help train new talents from both academia as well as industry to work in this new paradigm of carbon trade and carbon neutral reality. So NTHU, we're doing our part, looking at the future of energy, as well as the future of commerce and political reality. So I gave this background because I want you to know just how important these topics are. And today, we have probably one of the 4 most important and impactful speakers to share with us his insight, his expertise on these important topics. Professor Steven Chu is the William Kenan Professor at Stanford University, Nobel Prize winner, as well as the Energy Secretary under the Obama administration. That's only the tip of the iceberg. I'm sure there are many, many, many more. Everybody can ask ChatGPT, and I'm sure you'll get pages and pages of answer. So without further ado, let's welcome Professor Chu.
Thank you, Professor Gao. Okay.
Okay, great. Okay, all right, fine. Thank you. So I think I just want to start. Thank you for the kind introduction. And what I'll start with is just to remind you where we're heading. This is a temperature record from 1850 to June of this year, 2024. The goal, a UN goal of staying below 1.5 degrees centigrade since the beginning of the Industrial Revolution is passed. We will go above 2 degrees in the coming decade or two, almost assuredly. And so, but this is not really what's happening. We don't really know what's happening. The reason we don't know what's happening is because the oceans, which cover 70% of the surface area, the average depth of the oceans is about 3.7 kilometers deep. The bottoms of the oceans are very cold, a few degrees centigrade. The mixing time between the surface and the bottoms of the oceans is very slow, perhaps 100 years. So as long as it takes to warm up these, think of them as ice cubes in a glass of water, the weather, which is governed by the surface, land, and temperature, is hidden. The real damage of what we've done to the atmosphere is not going to be visible for roughly 100 years. Okay, so all the weird things you're beginning to see today are just the tip of the inverse iceberg. So that's one thing. We do know that human emissions, carbon dioxide, methane, and N2O are examples. This is a 2,000-year history of the human emissions. And you see that over those 2,000 years, it's relatively flat. And only in the recent 100, 150 years, and really only in the last 100 years, that it really began to zoom up. Okay, so the question is, where are we heading? This is a projection based on what we think would be various scenarios of how the world controls the greenhouse gas emissions. We're here now, and so in 2022, we emitted about 53 billion tons of CO2 equivalent. It's over 40 billion tons of carbon dioxide, and the rest of it in forms of methane, N2O, and other greenhouse gases. But those three are the major ones. Methane, let me go back. Methane is 84 times worse than carbon dioxide, but it oxidizes in about 10 years. And so then when it oxidizes, it becomes CO2. N2O, a different story. It's 300 times worse and lasts 100 years. And I'll talk a little bit more about that. So these are various scenarios about what will happen. Based on no climate policies, there are pathways of 2 degrees, 1.5 degrees, and things like that. The current policies, which we're not all following now, these are policies that countries have agreed to enact. And even if they enacted it, it's a different thing of saying this is our official policy and will the country actually do it. And so right now, in order to get there, we're heading to something like 3 degrees. You see that line that says net zero emissions. That means that emissions from everything humans do from agriculture and industrial processes, transportation, all those things, have to go to 0 by the end of this century if we're going to stay below 2 degrees. Another thing I want to point out is that we are expecting that as the climate gets worse, local agricultures will fail, and when local agricultures fail in fragile countries, the fragile governments might fail, and when the governments fail, then you have a bunch of refugees, either internal refugees within the country or within the continent, or going to other continents. And about 15 million refugees, 10 million refugees, let's say, streamed into Europe, and it totally changed the political landscape in Europe. And so it swung the governments to the right, some of them to the far right, because of this immigration issue. Now, here's, you may have seen this. This is a scenario, not a scenario, but this is how we understand that the human emissions are causing climate change. And these are simulations. This stuff in the blue, I'm not sure if there's a pointer. Doesn't matter. Does this work? Maybe this will work. Okay, there it goes. Okay, so here you have the simulated, if there were no human greenhouse gas emissions, this is what you would expect to see in terms of the temperature from 1850 to the present time, to 2020. And this is what we do see, and this is based on these computer calculations of the effect of greenhouse gases. Now, there are a few things I need to point out, and I didn't realize this 20, 25 years ago, but this looks like very convincing data that, yes, we understand what's happening in climate, but what you probably didn't know, and I didn't know this until maybe 10 years ago, is that these climate models are unstable, and they have to be hand-tuned so they don't go off. And so despite this very good-looking agreement, they're hand-tuned, and the models cannot predict precipitation at all with any reliability. They're pretty good at temperature, but precipitation they're not good at. Precipitation is very complicated. For example, and in fact climate itself is very complicated. For example, the role of water vapor, which is a very, very important, it's the most important greenhouse gas we have. But why isn't water vapor implicated? Because when the Earth warms up, water vapor increases. When the Earth cools down, water vapor decreases. Water vapor is considered a follower. It's not a forcing function. And so low-lying clouds block the sunlight, and they cool the Earth. When you have a cloudy day, you feel a little chilly. But the high-lying clouds actually have a very different effect. And this is a thermal map of the Earth emission, where you see over here, if there are clouds, these are decidedly a little cooler than over here, for example, in northern Africa, where there's very little rain, very little clouds. So it's very hot. So these are examples of this. This is another example. Let me see if it comes with music. So this is a real-time display, a little speeded up, and a composite map of the cloud formation, what's really happening in precipitation. And this is in what we now call, this is a new term that you may have heard of called atmospheric rivers. And atmospheric rivers are little thin, very long streams of high moisture content, and that's an atmospheric river you just saw colliding into California, the west coast of the United States. This is, just in case you don't know, this is California, and this is the Bay Area. So this is an atmospheric river of February 2017. It was torrential rainfall where I live. And in fact, the rainfall was so torrential that a very significant dam was in danger of being breached because of the overflow of water, and they evacuated 180,000 people for a couple of days because they thought that that dam would break. And in fact, it was starting to break during this time. You've probably seen headlines in other places around the world where you see these torrential rains, pile up of cars in Spain, Valencia, and other places. So this is seems to be becoming more frequent, but we actually don't know because part of me does little weather statistics on what's happening. And it's very hard to discern, is this real or is just our imagination, because reporters like to tell us, the sky is falling, literally, and these are storms. But anyway, all right, that's interesting. Okay, lost in translation. So how do you get rid of all the greenhouse gases? And part of it is what you have to ask, where is the emission coming from? And you see that electricity production is only a sector of it. If you look at agriculture, forestry, land use, and other things, you realize, I hope, at least most of the other words will come out, that in order to eliminate all the greenhouse gases, that means you have to eliminate the emissions that are produced in making steel and concrete, plastics, chemicals, textiles. The food supply chain is 1/4 of all greenhouse gas emissions around the world. And people don't even talk about that. And so that's a real issue. Also, I wanted to give you a little bit of history. The study of history is important. It puts things in context, it gives you perspective, and also it's well known that those who don't study history are doomed to repeat it, but yet those who do study history are doomed to stand by helplessly while everyone else repeats it. So, with that historical context in mind, I'm going to tell you that most of the revolutions we've seen, the agricultural revolutions, several, the industrial revolutions, they all came from technology. They came from brilliant science and inventions. For example, you all know, hopefully you all know that of the invention of the transistor that occurred at Bell Laboratories in 1947. It's a year before I was born. Show you how old I am. And this is the point contact, very famous transistor, first made by John Bartine, Walter Bertin. These were people in a research group led by Bill Shockley. They didn't tell Bill Shockley what they did, and so Shockley's name is not on the original transistor patent. In fact, after that occurred, Shockley, who's not a nice person, took both of them in his office one at a time and said, sometimes the people who did the work aren't going to get the credit. I'm going to make sure I get the credit. But he then locked himself in a hotel room. He was the eminent condensed matter physicist in the United States at the time, and he, over the period of 2 days, essentially developed the theory of the transistor, of semiconductor physics. So he laid the foundations for semiconductor physics because he was so angry that he wasn't part of the original invention. So his name, and he shared the Nobel Prize, deservedly so. However, let me just point out that it was not the invention of the transistor, it was the invention of the transistor and the ability to make silicon and germanium ultra pure. Once you made it ultra pure, you could put in impurity ions and dope them. And it's the doping of the transistor which actually led to its commercialization. And this is a picture of Bill Fan, also Bell Labs, making what's called zone refining high purity germanium. Also, other people, Teals and Sparks at Bell Labs, did the same for the having a seed crystal and slowly growing it, pulling it out. So it's the ability to make ultra pure semiconductor material, germanium and then silicon, that led to this transistor revolution. Another Nobel Prize, Charles Kao gets a Nobel Prize for optical communications, but it was the ability of Corning and Bell Labs to make the fiber so pure you could send light over very long distances without absorption and scattering that led to its commercialization. And finally, the silicon photovoltaic cell, also invented at Bell Labs. You might ask, what was not invented at Bell Labs? Not much, as a former employee of Bell Labs. It's years of improvement of this technology that made it so important. Okay, so let's return back to the overall energy. These are graphs of how solar power, photovoltaic power, offshore wind, onshore wind, it's declining by a lot. I don't expect you to read the fine print, but just know that in a period from 2010 to 2019, photovoltaic solar cell modules decreased by 82%, 1/5 of what they used to be. Offshore wind declined by 38%. Nuclear went the other way. It increased by 1.6%. I'll talk a little bit more about that later. And then what happened? Okay. New materials development. Silicon has ruled the photovoltaic world for a half a century, but there's a new kid on the block. It's called perovskites. These perovskites have a promise of having higher efficiency, much less energy input to make this material, and already these perovskites have a very, very rapid development curve. And so the question is, will they take over from silicon or use in tandem with silicon to make much more efficient photovoltaics instead of maybe 21, 22%, which is what is commercial single crystal silicon photovoltaics today. The highest crystalline photovoltaics, the kind you send out into space, is about 25% efficient. These things promise to go to over 30% efficient. So very, very rapid development. We don't know. Again, this is the materials development that is a big deal. We also are seeing big developments in the ability to transmit electricity across large distances with very little energy loss. This is a picture of a 12 billion watt, 3,000 kilometer long DC voltage in China. And it sends over this 3,200 kilometers about 5% energy loss. So very, very efficient. And so as you get more and more renewables, you need to be able to port this over large distances. And so this technology is also very important. Okay, so we also need a fourth industrial revolution powered by carbon-free energy. But let me tell you some of the problems that we're beginning to see, for example, in California. California today is about 70% electricity generation that's carbon-free. 10% of that is nuclear. The rest is solar, wind, geothermal, and hydro. And so this is California, May of 2024, and noontime is over here. And so what you have, this big yellow blob, is an abundance of solar power. We're going to add more solar power than even what we have today. California plans on getting from 70% to 80, 90% within a decade and a half. And so what is happening is, at this point, you're producing more electricity than you can use. And so the price of electricity goes to zero or negative. That means you're paying people to take electricity off your hands. And so what happens is, because of that, California has installed huge amounts of battery, very expensive batteries, but because it's negative pricing, you can afford to say, okay, I can take this, you're exporting this stuff is being exported out of California, but we're oversupplied, but you're charging batteries. And so the heat load, the electricity load peaks not at noontime, but around 3 or 4 o'clock when you have air conditioning at its very worst. And so this problem is called the duck back problem. Why? Because it looks like the back of a duck. And in 2023, it's beginning to dip to negative, and now we're solidly in negative. Take the electricity, or we'll warm up, you use it to warm up the ground. All right? So this is what's happening, and because of that, you can take very expensive batteries and say, okay, I can put the energy into a battery and then use the battery to turn on at high demand around between 4 and 6 o'clock. This, by the way, is a huge problem. And when you see this ramp up going from 5 p.m. to 6 or 7 p.m., this is gigawatts. And so this, we're talking 10 gigawatts in an hour. So not only do you need energy storage, you actually need the power from the batteries to supply that 10 gigawatts. Now, the way electricity is priced and used in the United States is the following. This is an example of the summer between 2010 and 2012. These are successive years. This is the cumulative generating capacity. And so what gets dispatched first, what gets used first? Well, the stuff that has no real additional costs, so anything renewable, wind, solar, the fuel is free, and so it's in the CapEx, and so that's always first. And then as you march along, this is in the East Coast, you begin to turn on other sources of energy. As you go, you next turn on coal. It's polluting, but it's cheap. And then you go to natural gas and you turn that on. And what happens at this point? At this point, you run out of generating capacity. And then you have a looming blackout. And then the price goes way up. So instead of being $50 a megawatt hour, it goes to $300, $1,000 a megawatt hour. Okay? So now, the issue is, can consumers, both companies and the private sector and homes, be motivated to say, when you have these near blackout conditions, you're running out of generating capacity, would you be willing to turn off your air conditioning for a couple hours? Would you be beginning to not run your dishwasher, your washing machine, and other things? And the answer is yes and no. Intelligent people might say, oh, you know, because if you're going to charge me what it really costs the power companies, and it's now gone up by a factor of 10 or 100, of course I'm not going to use electricity during that time. But the less educated people won't know about this, and then all they see is their electricity bill going up. So before you have real-time pricing, you have to make it automated. So the less educated people, their washing machines and things just turn themselves off. And so that's one of the issues. But that needs to happen because this so-called peak load shedding is becoming very important. A couple of years ago, 2 years ago, California avoided a very, very serious blackout when the government went out and said, we're going to head for a blackout. Please, please turn down turn out your air conditioning. Don't think of using electricity just for this one afternoon. And blackouts were avoided. Okay. So there's other things that I could talk about. This increased storms and earthquakes mean this electrical system becomes much more vulnerable. As we move to electrification, we become much more vulnerable to power outages. When I was a kid, and even now, let's say you lose electricity, we have a gas stove and you still can cook. And you can still have hot water because it was a gas. Okay, suppose now you have an electric stove, you have a heat pump for your heating, you have all this other stuff. You run out of electricity, you're losing it. And let me remind you of a blackout that occurred in 2003. There was it started locally. There was a faulty relay that happened to be in Canada, and that failure caused a transmission line to disconnect. But once this thing disconnected, the other lines became overloaded and caused a cascade. And so this is a picture of August 14 and 15 in 2003, and part of the United States in the East Coast. This is the New York, Pennsylvania metropolitan, and the whole area became black. The odd thing about this power failure is that there were precursors. If you look at, this is not in real time, but in the post-mortem of what was happening, you begin to look at the phase getting out of sync, and it was occurring over several hours. So there was actually, if you had an early warning system, if you knew what was going on, and you could redirect power in such a way, you could have avoided this massive blackout. We have the technology to do that in principle. There are things they're called phaser measurement units, or PMUs. They measure the voltage and the frequency very precisely, 30 times a second. When I was Secretary of Energy, I used a lot of money to enable utility companies to buy these automatic systems so you can report and you can coordinate what was going on in the grid. And unfortunately, for the first 2 years, I gave them to the utility companies. The utility companies viewed this as their confidential secret information, and so they weren't going to share this with the other utility companies, and defeated the whole purpose of getting a system that you knew what the grid was doing. And so in 2012, I called them in my offices. I gave you these things for free because I wanted a more robust electrical supply system, and you're hiding them from each other. You better start sharing the information. I'm going to do something really serious, and you'll be sorry. This is the secretary in a conference room talking to about 20 electricity executives, and they began to share the system. And then since then, you could see there was a little power outage in Florida, and you can see the ripple go across the United States to Canada and come back. And so now, why do you want to see these ripples? Because we have the ability to port electricity, not just by putting voltage up here and letting it trickle down, but you can actually have active, for engineers, this is called impedance control, changing the inductance and capacitance, and not resistance, so you can actually ship the energy over here and this wire over there and another wire. In the olden days, it's like water. You pour water at the top and it just trickles down by gravity. You have no control, except by shutting off different valves here and there. But now you can actually say, no, I want the electricity to go here, not there. So it's a technology, but most electrical systems do not have this installed yet. Okay, I want to talk a little bit about material resources. And you ask the fundamental question, of all the stuff in the ground, what is really happening? And it turns out, of all the things we use from the earth, the biggest buckets are in two forms. One form is concrete, asphalt, cement, and building material and wood. This is on the amount of metric tons per year used. This is every tick mark is 1 order of magnitude. And on the other side, it's fossil fuel. Below that, this blue stuff, are plastics made from fossil fuel, oil, natural gas. Then, besides steel, then you have to dip 2 orders of magnitude before you get to the other material we yank out of the ground, namely aluminum, copper, zinc, and so on. And so, just think about that. Most of the stuff we haul out of the earth is either energy or building materials. So, let's talk about that. Not anytime soon, maybe within 50 years, certainly within 100 years, but probably 50 years, we're going to run out of copper. Didn't know there was a copper shortage. Well, there is not yet. And so one of the things that's a challenge that I've been talking about for the last half dozen years is that the fossil fuel stuff, we got tons of carbon. If you can make a carbon conductor, and there are high conducting, very strong, lightweight carbon conductors that are as cheap as copper, then you have an unlimited source of electrical conductors, but we don't know how to make them commercially. So any of you young people who have an engineering or science bent, figure out how to make high conducting carbon cheap. There's other things, but anyway, let's move on. And even with cost-effective utility-scale batteries and hydrogen, we're going to need some turn-on sources. And the turn-on sources, we have several choices. You can turn on fossil fuel, coal and natural gas. But then if you do that, you have to capture the carbon and you have to sequester it. But when you capture, you're only capturing 90%. And the mere act of prospecting for natural gas, about 2 or 3% leak out of the ground that are not recovered. So it's not carbon-free to say I can use natural gas and just capture it. You're at least 15% of it goes into the atmosphere. The other possibility is fission or fusion. So let's talk about fission. Microsoft this is a picture on the left-hand side. This is 3 Mile Island. There was a big nuclear accident at 3 Mile Island. One of the reactors partially melted down. It's damaged, it can't be started. And so 2 of the reactors went offline. One of them was not damaged, but it was turned off later because it was not economical, because they couldn't bid against the very low cost of solar and wind or natural gas. So it was closed, and they had only 2 operating. Microsoft is now paying over $1 billion to restart this power plant. What? They want to use all the electricity for artificial intelligence data servers. There are other companies. If you look at the biggest companies that use artificial intelligence, Microsoft, Meta, / Facebook, Google, Amazon. Each of those companies have orders of magnitude more compute power than all the US universities combined. Any one of those companies. Okay, think about that. I mean, there's a lot of computer power in universities, at Stanford and MIT, other places. And it's now, their compute facilities dwarf this. They are either going to nuclear reactors, large ones, or small modular reactors. But, and this is a resurgence in the United States because this is a perfect customer. They want power 24/7, and they want it carbon-free. Now, what's the problem with nuclear? The problem with nuclear is we've forgotten how to build nuclear power plants on budget, on time. This is what happened. This is in the United States as you go into nuclear reactors, and the cost is coming down, 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 and oops, something happened. And why is that doing that? Okay, so oops, something happened. What happened is about here, 3 Mile Island happened. And when 3 Mile Island accident happened, the NRC said, ooh, we have to improve these regulations. There was an anti-nuclear thing that rapidly grew, and all of a sudden there were new regulations put in place. At that time, it took about 10 years to make a nuclear reactor. And if you ever do anything in business or in home remodeling, once you have a contractor and then you say, oops, I want to make a change, they hear change order, and to a contractor, that's ka-ching, because the price goes up. Okay, so the price went up, and didn't not only go up in the United States, it went up many, many places around the world. But it's more than that, because these nuclear reactors cost, at that time, $10 billion for 1 gigawatt nuclear reactor. That's pretty serious money. You have a factor 2 overrun, $20 billion? That would bankrupt a utility company. And many utility companies did go bankrupt. And so that's another issue. If you have something that's this capital X intensive, you cannot be over budget or over time. Okay, so anyway, let's talk about nuclear safety. And one of the things is, let's make an estimate of how many deaths per unit of electricity energy you've made per terawatt hour. And the worst is brown coal. It's over here. This is 32.7 deaths per terawatt hour generated, followed by coal. Brown coal is lignite. It's got high moisture content, very polluting. What are the deaths from? It's from air pollution, particulate matter, SOx, NOx, but mostly particulate matter. Oil, biomass. Where's nuclear in this? It's down here. It's a little safer than wind and a little bit less. Why is it doing that? It's a little safer than wind. It's not as, but it's orders of magnitude safer than conventional forms, and it's 100 times more safe than burning wood chips in, let's say, a commercial power plant in Denmark. Okay, this is the amount of danger you're exposed to. But let me give you a more realistic appreciation of that, because there is this fear of radioactivity, and what most people don't realize is about 1/3 of the average radioactivity you're exposed to that's not medical. If you get a CT scan, you get a big exposure. Dental x-rays are okay. It's okay. Don't worry about dental x-rays. It's in the food you eat. So not only are you being exposed to it, you're ingesting it, and it is in your body. And all the radiation gets captured by your body. And so because of that, there's a new unit of radiation. It's called a BED. It stands for banana equivalent dose. How much radiation you get from eating one banana. And in Asia, I gave a talk in South Korea. It turns out BED can stand for a bok choy equivalent dose. A cup of cooked bok choy is about the same as one banana. Okay? Why is it radioactive? It's not because of H-bomb testing. It's because it has potassium that's naturally there, made from the supernova or neutron star that made the stuff that formed the Earth. Okay? So does it mean you stop eating bananas or bok choy? Well, then you better stop eating spinach. You better stop eating a lot of food. Potatoes, carrots, red meat, these are the equivalent doses for one serving of that. Now, is it dangerous to you? No. The Food and Drug Administration, the NIH, says no, continue to eat your vegetables because it's much better for you, and there's no evidence that factors of 4 or 5 in background radiation at this level have any statistical correlation to any kind of cancer. Okay? So it's completely safe at this level. Now, if you're 100 times higher, that's a different story. If you fly from Taiwan to New York, well, let's not say Taiwan, let's say Korea, Japan, to New York City, you follow the polar route. The magnetic fields don't shield the cosmic radiation, and you get, and a few round trips, you get a significant dose of radiation. In fact, the pilots who fly in those polar routes are near the limit imposed on people who work in nuclear reactors. But no more incidents of cancer among pilots. Okay, so I don't want to get you alarmed. Don't be a pilot for Korean Airlines. Okay, what about fusion? So this is all to say that fission is safe. There is one issue, and it's a significant issue, is what to do with the spent fuel, the waste, and where do you put it? And so there are new technologies being developed, boring hole technologies, so that if you want to put it, you have to put it underground in a repository. I'm an advisor to a group that's developing some of this technology to see that if you can put it underground safely without making a labyrinth of tunnels that humans have to go. So the hope is that the expense of having unmanned repositories put there by deep borehole drilling would decrease the cost and make the number of accessible sites much bigger. Again, it's not completely proven, but there are technologies going on. What about fusion? Well, there's magnetic fusion. This is a picture of ITER. And will fusion, magnetic fusion, ever be commercialized? And the answer is we don't know, because there are unsolved problems. The neutron damage and the materials for these reactors is an unsolved problem, and the material will crumble after a half a dozen years. And there is no, it's not a physics problem, it's a material science problem, and unlike physics, material science proceeds by mostly shake and bake. Try it and see what happens. And so until this is, until we figure out how to do the materials damage, magnetic fusion is not going to work. There's the spectacular success of Lawrence Livermore Laboratory that had the first break-even fusion. Break-even means the energy hitting this gold reflecting hollow realm surface. It's a cylinder with little holes, and these multicolored things are laser beams, and they create X-rays that implode the deuterium and hydrogen. This broke even. You got 3 in the first spectacular success. There were like 3 or 4 hits that exceeded break even. 3 megajoules. 3 megajoules is 2 candy bars worth of energy. Okay. There's a shot, 1 or 2 shots a month if you're lucky. They had 4 successful over a decade. I'm good friends with the person who led the charge to get this to happen, and this is very delicate. This is the sphere. It's a diamond sphere of where you put in tritium and deuterium, but it has to be single perfect crystals, so you have to anneal it several times to make it perfect. It's held as suspended in here by a 50 angstrom thick polymer film on both sides, and you have to hand hold it and just carry it around very delicately, and still you lose half of them. A commercial unit means you have to shoot 10 or 20 per second into a chamber which had a nuclear explosion a tenth of a second before, and so there's lots of swirling debris and stuff. And so the prospect of the engineering hurdles of getting this are formidable. So the estimate of the deployment of commercial fusion, when I talk to my friends who are real fusion experts, are somewhere between greater than 40 years to never. Commercial fusion. I have a joke about that. We can deal with the joke in question and answer period. Okay, so anyway, there's a rapid growth of electricity, EVs, data centers. You just heard in the introduction about data centers, so let's talk about what the projections are. This is the energy, this is a paper written in 2015, plotting the energy of data centers, wireless communications, other things. The green are the data centers, and projecting by 2030 that about 20% of the electricity will be gobbled up by communications and data centers. This was just as artificial intelligence was beginning to turn on. I should also mention that cryptocurrency used to use half. They're trying to make it more energy efficient, but it's 1/3 to 1/2 of all the electricity used in data centers are to mine Bitcoin. And the first applications of Bitcoin are money laundering and tax evasion. So I'm not a big fan of Bitcoin. But anyway, so this is happening. It's commercially viable. And as I told you, the biggest data center operators are now beginning to look to nuclear to store the electricity. They can't get enough electricity any other way. Although ExxonMobil is saying, no, we'll give you gas-generated electricity, we'll capture the carbon. But they capture the majority of it, but it's still got a problem. So what's the issue with data centers? There are two issues. One issue is how do you train the models? And so what they do is they scrape everything off the internet, and they are actually talking, if you go from ChatGPT 3 to 3.5 to 4, there's a number of parameters, and the number of parameters is like 1.8 trillion parameters to fit to this artificial intelligence models, okay? This is kind of crazy. They've actually mined all they can mine, so the amount of data is asymptoting and until they have new sources of data. And again, in question and answer period, I can tell you how that will happen. But in any case, let's compare it to another kind of computer. Here on the left-hand side, you see what appears to be a 3 or 4 year old little child who can recognize a cat. The big artificial intelligence breakthrough was you could use artificial intelligence to tell the difference between cats and dogs and fire hydrants. It was made by Fei-Fei Li at Stanford. Big deal more than a decade ago. She doesn't need nearly the amount of power to do this. This toddler, in terms of, you can talk in terms of calories, or you can talk in terms of watts. 70 watts of food power, solar powered. Solar is because food's grown by the sun, of which half of it goes to feed the brain. Remarkably, a 4-year-old has as much calories feeding her brain as an adult does. But they're learning much faster than an adult. And over here you see someone else doing experiments due to gravity. So they don't need all those parameters. They figured it out on their own with far, far less data. So this tells you profoundly we are missing a lot of what really makes intelligence. We don't care if it's artificial or not. And so a big goal is to try to understand how we can make computers like human brain computers, which are so much better in many things and for far less data. Okay, so there are other ways of doing it. One of the ways is that the people who make artificial intelligence, the people who make the chips, NVIDIA, for example, are highly motivated. The algorithms are getting better and better because if you're going to 30% going to 40, 50, some people saying, you know, by 2050, maybe half the electricity of the world is going to be used on data centers. That's not sustainable, especially since we're moving also into EVs and heat pumps. And so the question is this industry going to be self-limiting, or can they figure something out? There's, so the short term are algorithms, better, more efficient chips, things like that. The longer term is a better computer architecture, or the fundamental stuff. There are new materials, perovskite ferroelectrics. Ferroelectric is you use an electric field to align spins, and then you don't have to use any more power. So in memory, you can have a spin flip at atomic level from, you know, plus and minus. And once you have two states, plus minus, you can have logic chips. And a friend of mine who I recruited to head the Sunshot program when I was Secretary of Energy is now the Vice Provost for Research at Rice University, founded Kepler. It's a company, Kepler Compute, trying to commercialize ferroelectrics as a new generation that perhaps will replace CMOS silicon. Whether it works or not, don't know, but lots of people are very focused on decreasing that. Okay, energy storage is absolutely crucial. There are lots of versions of energy storage, but the thing I want to focus on is very large scale. PHS is pumped hydro storage, and this is other forms of molecular storage, let's say hydrogen and synthetic methane and other things. This is my favorite form of energy storage. Let me explain how it works. When the sun shines, when the wind blows, you pump water, let's say for irrigation, or you pump water from low altitude, high altitude. What's low and high altitude? It's 100 feet. And then the turbines are so efficient that when you let the water back down, you have a round trip efficiency of 75%, and 95% of all energy storage is pumped storage. And it is, if you have an existing dam, it's by far the cheapest battery you can imagine. And so the question is, how do you get more and more pumped storage? But that's still limited geographically. Talk about hydrogen. There are various colors of hydrogen. Gray hydrogen is you take methane out of the ground. There's a process where you can convert methane into hydrogen and CO2, and you vent the CO2. And that's in the United States, where there's a lot of natural gas. It's pretty inexpensive, $1.50 a kilogram. Blue hydrogen is you take the hydrogen, you capture 90% of the carbon dioxide, you sequester geologically somewhere, and that's about double in price. And then green hydrogen is you use very clean electricity, solar, wind, nuclear, and that's another doubling of the price. And these are the prices at the site you use the hydrogen. Let's say oil refineries are the biggest sources or biggest consumers of hydrogen at the moment. Having said all this, hydrogen is good. It can help decarbonize steel, plastics, chemicals, fertilizer, aviation fuel. It can be the stepping stone to make synthetic aviation fuels. If you're going to make hydrogen from electrolyzers, we don't know how to scale this because we use precious metals, so that's an issue. Hydrogen is very leaky. And leaky means it comes in, first it makes, you can't use it in natural gas pipelines, it will leak out. You can have 5%, 10%, but other than that, it can't be leaked. And hydrogen in the atmosphere in substantial quantities actually preserves methane longer, so it's effectively like a greenhouse gas. And so the trouble with pipelines is we have no way of detecting remotely hydrogen leaks. There's no good optical signature for hydrogen, unlike methane, unlike CO2. And so that's an issue. But there are technologies emerging. For example, another person I recruited to come join me at Department of Energy, his name's Ravi Prasher. He's now the Chief Technology Officer of Bloom Energy, which makes hydrogen solid-state fuel cells. And they can now make these fuel cells 70% electricity efficient. That means hydrogen converted to electricity 70%, or the opposite, electricity converted to hydrogen. So electricity converted to hydrogen means you don't have to ship them over pipelines. You can have electricity, send them to the oil refinery, the steel plant, make the hydrogen at the site. And so if these solid oxide fuel cells become commercially viable in terms of the cost, which I think they will, this can transform and really make hydrogen more likely. There's all sorts of other forms of hydrogen. What's captured the imagination and the attention of oil companies and also startup companies is the possibility that you can mine hydrogen geologically. Now, hydrogen, I said, was very leaky. There's one source of hydrogen, natural source, that actually pops up, but the expectation is most of the time it just leaks out into the atmosphere. But if you inject water into deep underground rock, rock that contains rich in iron or manganese, and in this case, you're changing the oxidation state of iron from 2+ to 3+, you actually produce hydrogen. And so by just injecting water deep underground, you can produce hydrogen when you want it, and that's a big deal. Oops. Another thing disappeared off the slides. Never mind that. Doesn't matter. And so let's go to other forms of energy storage other than hydrogen or pumped water, and that's commercial batteries. This is the scale of commercial batteries: energy per unit weight, energy per unit volume. This is the Tesla battery, and great progress is occurring. Let's see if I can do this. There we go. This is where I think batteries will be within 10 years. It's not a completely idle prediction. I'm on the board of directors of a commercial battery company, and we're shipping out samples that are doing this. They're more expensive than the other batteries, but essentially the batteries, we're going to expect them to double the energy density per unit weight and energy density per unit volume. And so that's a big deal, because when you double the energy density per unit weight, that means an electric vehicle with a 350 mile range will weigh the same as an internal combustion engine car, let's say 2-liter car with a transmission and a fuel tank. And so when the battery, which is now 1,400 pounds, is 600 pounds, it's a big deal. You need less of a battery. Let's see. The energy density is likely to double. The cost is dramatic. This is a learning curve. On the x-axis is whenever you double the production and ship them out, you get better at manufacturing, and so the cost begins to plummet. And so this is the start of Tesla EVs, and you see the cost is plummeting. It's a big deal. In year 2000, lithium-ion batteries cost $2,000 a kilowatt hour. Today, they're about $100 a kilowatt hour, and by 2030, $50 a kilowatt hour. Again, because the OEMs, the car manufacturers, say, I don't want to pay more than, let's say, $100 or $90 per kilowatt hour today. And so this is coming down. But then there are other resource issues, for example, cobalt, nickel. And the answer is cobalt and nickel are already becoming too expensive, so they've gone to iron phosphate, which means lower energy density. But there are other technologies to boost the energy density. What about lithium? I already told about the copper shortage. It turns out it may be possible to mine lithium out of salty water. If you drill for oil, for example, you find oil. Oftentimes, most of the time, you find natural gas, and you also find water. That very salty water has a lot of lithium in it, much higher than, let's say, seawater. And this is Chung Lu, who's a professor at University of Chicago, who did a postdoc with me. She was a grad student at Eastway at Stanford, and she developed methods to take lithium out of salty water, even seawater, and with great progress. Okay, batteries. Remember, lithium is okay for a couple hundred years if you can get it out of salty water. But copper we still have an issue with. But iron phosphate, you can go even higher energy density if you use a very earth-abundant material called sulfur. And the sulfur, right now the battery energy density is about 250 watt-hours per kilogram, going to about 400 to 450 within 5 or 10 years. But you can go much higher than that if you use sulfur in principle. And you use metal, metal lithium instead of lithium in graphite, which is used today, now transitioning to lithium and silicon, which is higher energy density. And this thing has a mind of its own. What happened? Definitely has a mind of its own. Where is my lithium? Very sensitive. Here we go. Anyway, my group, a person in my group, I have a really weird group of one person per topic, one person per field. If you get the right people, you can do this. Thank you. And we're trying to invent an interface material that prevents dendrites from forming. And so the idea is if it's a very strong material that really passes lithium, you can prevent these dendrites and go to a metal anode, which will increase the energy by a whole lot. We have some preliminary results, but until it's reproducible and rock solid, I can't really talk about it. Agricultural revolution. We need a fourth agricultural revolution. Let me remind you what the third agricultural revolution was. It's the ability to make nitrogen-based fertilizers from ammonia that actually ultimately comes from nitrogen in the air. And it was recognized, it's called the Haber-Bosch process. And for that, Fritz Haber was awarded a Nobel Prize in 1918. They gave Carl Bosch another Nobel Prize in 1931 for the Haber-Bosch process. So they just had to think of another reason for giving it to him, and said he gets it for high pressure, high temperature processes to make nitrogen, which was the Haber-Bosch process. So it's just correcting an oversight. That's part of the Industrial Revolution. The other part was use of plant breeding to increase productivity. This is Norman Borlaug, who got a Nobel Prize for his work on breeding high strains of wheat. And here you see the different sizes of the wheat kernels, very much more productive. The combination of those two things meant from 1961 to 2021, the amount of land put in cereal production. Cereals are wheat, corn, oats, stuff like it, rice. And the amount of land put under cultivation did not increase, and yet the cereal production increased threefold, but all over the world, because of this agricultural revolution. But there are issues. One of the issues is there's a lot of greenhouse gas emissions from the food we eat. And over here leading the list are beef. Beef emit a lot of methane. It's mostly burping. And so there's a big effort to produce more polite cows genetically. Meaning that you introduce microbes into the cow. These microbes are parasites. They're not symbiotic with the cattle. So they steal the food and they make methane. And so there are ways of trying to look at how you can stop that. And if you look at this list, there's beef dairy herds. Milk also produces a lot of methane. Pigs turn out to have less than 8 times the greenhouse gas effect of beef. And then you go down the list, and of course you get to grains like rice meal and everything. Okay, so this is what we're up against. If you compare the greenhouse gas emissions of the world, this is a little out of date. This is 2020. China has now doubled since then. But if beef and cattle were a country, they would have more greenhouse gas emissions than any other country except China, and including the entire European Union plus Great Britain. Okay, so lots of greenhouse gas emissions. And so you can't tell people not to eat what they want to eat. That's political death. It's like raising taxes on gasoline. And so you have to just make more polite cows. Now, one of the things you can't do is get rid of fertilizer. Fertilizer, 3/4 of the nitrogen N2O, nitrous oxide, is from agriculture. And this fertilizer, you know, when you have fertilizer in the ground, what the plants don't pick up, they're turned by microbes into N2O, and it comes out of the soil. So you can't even trap, you know, you've heard of algae runoffs from the N2O that goes in the water stream, but it's the N2O that goes from the soil in the ground directly in the air. 3/4 of the plant food is missed by the plant. And so there is a technological opportunity. It's called synthetic biology. And the idea here is you have microbes that enter into symbiotic relationships with plants. It was inspired by legumes, which enter into symbiotic relationships. And so these microbes are right next to the border of the root. And so they supply food to the plant, and the plant somehow keeps the microbes happy. And so then with this, you use less fertilizer. In this company, Pivot Bio in the Bay Area, they arranged for microbes that decreased the fertilizer of corn by 1/2. But it took too long. It took 8 years. And the company's nearly bankrupt, and the company that supplied the synthetic biology did go bankrupt. So the issue is, can you make this so that, and it only works in some soils because microbiomes of soils are different. So you need the development time not to be 8 years, but 2 years or 3 years. And then you can maybe do this. Again, it's a technology challenge. Okay, we're gonna likely go over 550 parts per million. I mentioned all the steel, chemicals, and plastics. And I also said we're emitting 52 gigatons per year. And based on agriculture alone, we're gonna have to capture 10 to 20 billion tons a year of carbon dioxide. Okay, let's think of the scale. All the landfill, solid waste landfill in the world is 2 billion tons. The carbon dioxide, when you pump it underground, it has a density of about 70% of water, which is much lower than landfill density. And so you're talking about a volume of not 2 billion equivalent tons, we're talking about 40 times, 50 times of all of landfill per year. And it has to continue for decades. Okay? The only place that you can put this stuff is actually deep underground, because remember, we've yanked that stuff out of ground in using fossil fuel. Now, capturing the carbon is expensive. When I was Secretary of Energy, I funded a carbon capture pilot plant called Petronova. It captured about 25% of a medium large-scale coal plant. It cost $1 billion. It was the first carbon capture project that was on budget, on time, but it uses 30% of the power of the coal station to actually capture and release the carbon dioxide. So it's hugely capital intensive. That's the size of a large pickup truck. This is 1/4 of one coal plant and $1 billion. Okay, so this doesn't have money making written on it. And if carbon dioxide is $100 a ton, nothing's going to happen. It's got to be $200 a ton. There are other methods being developed. One by a company, Svante, been on board of that for a decade, using what are called metal organic frameworks, and you have amines attached to it. But both of these, both the Petronova plant, which uses amine in a liquid or a nanoparticle form, or this, means the carbon dioxide forms a chemical bond with the amine. In order to release the carbon dioxide, you've got to break the chemical bond. And so that's an unavoidable use of energy. And so if you ask, as a physicist, what's the minimum energy you need to capture carbon dioxide from, let's say, a coal plant, a cement plant, or from the atmosphere? And it turns out it's a very simple calculation, but it turns out you don't need that much. To capture energy from a coal plant, you only need 5 kilojoules per mole of carbon dioxide. From the atmosphere, 19.4 kilojoules per mole. But what are we now using? To capture air, we're using 300, 400 kilojoules per mole, okay? Not 20. And it's because you're making these chemical bonds. Once you make a chemical bond, you've got to break that chemical bond. And so, I don't know how much time I have left because I'm not sure when this started. I'm going to very briefly tell you about a project we've about to submit this paper. It's a new method of capturing carbon dioxide. This is one of my postdocs, Sang-Jo Kim, collaborating with a postdoc with Arun Majumdar's group, and it works as follows. We know that when water is very, very alkaline, that means the pH is very high, pH of 10, 11, 12, you can put a lot of carbon dioxide into water. The way it goes is carbon dioxide goes into the water, it gets dissolved, it turns into carbonic acid, which dissociates into protons and bicarbonate, further energy makes it go into other forms. And so if you take this high pH, very basic stuff, and turn to pH about 5 or 6, the solubility of carbon dioxide in the water drops by more than 3 times 10 to the 4 times less. So by just changing the pH, you can drive the carbon dioxide out of water. So that's great. So chemists and electrochemists said, I'm going to try to change the pH. pH is, the number of protons in solution. But whenever you go from low concentration to high concentration, there's a thermodynamic penalty. Remember, entropy wants to go from high concentration to low concentration. Going the other way, you have to pay that price, and there's no violation of the second law of thermodynamics. So going from low concentration CO2 to high concentration, you have to pay an entropy price. Going from low proton to high proton, you have to pay an entropy price. And that's a big deal. And so you can calculate easily the minimum energy is about 0.059 volts per pH. This is a pH change of 7. It's a big deal. So what we stumbled on is a way to change the pH without changing the proton concentration. Now, how did we do this? Well, we got lucky. We put an amine on our molecule and say, it captures carbon dioxide, it releases carbon dioxide. So you do the next thing. You just want to prove that the carbon dioxide is attached to the amine. So you do what's called mass spec. And you say, okay, I want to see the mass of the amine molecule increase by 1 CO2. No CO2. But the pH is changing. And how can you change the pH without changing the proton concentration? Okay? Because you have to look at the fine print. pH is defined as minus the log of the proton concentration times the fudge factor, called an activity factor, which was invented about 100 years ago. So it says when you're at very high concentrations of stuff, the high concentration can either hinder the effectiveness of the number of molecular species, or it can help it. But there's no insight. It's just a fudge factor. And so we got lucky. The pH definitely was changing by 7.5, but we weren't paying the energy penalty by at least a factor of 20. And that's the minimum energy. So it had to be different. So let me explain to you, why does it do that? This is a very temperamental little machine here. Okay, this is this molecule. The blue is nitrogen, the red is oxygen, and this is a molecular dynamics simulation of water molecules. The water is H2O, so the red is oxygen and the whites are protons. And so when you put this in an oxide state, it becomes charged. And then so the oxygen is pulled a little closer to the charged molecule, and the hydrogen is pushed a little bit away. But not enough to make free hydrogen protons. Because if we did that, we would have changed the proton concentration and would have had to pay entropy penalty. But suppose you look at this, and look at this chemical reaction. It takes a proton plus bicarbonate, HCO3 minus, and it makes HCO3 neutral plus an OH, and it finally becomes CO2 plus water. Okay, that uses up a proton, but it wants to maintain a chemical balance. You've used up this proton, and so what happens is that proton next to the charged molecule is easier to donate a proton from this guy than from normal water. So you haven't changed the proton concentration, but when the protons get used up, there's a supply of protons that say, oh, you used up one of these guys, have another one. Okay? It's like you're gambling. Yeah, you just lost a little money, have another few chips. Your stake remains the same. And so what happens is this these polarized water molecules get to donate the proton. And how do we know this? Well, we take these polarized molecules, and it's in this acid, and then you throw in OH, KOH. Sorry, I'm one slide ahead of myself. This is the degree of oxidation. We said when we have more oxidized molecules, more polarized molecules, the pH changes. So the gray is pH, and the orange is the number of protons. So it scales. And so the idea is you expose water to very basic, you expose carbon dioxide in very basic water, it goes into solution, you make it polarized. When you make it polarized, you have this source. And then CO2 comes out. When you take an electron off this molecule, it requires energy. But in the round trip on the way back, it wants to grab an electron, and if it's pH independent, the round trip energy you need is 0. The only energy you're using is resistive energy. And so how do we know this? When we have a bunch of polarized molecules and we throw OH into it, you think OH, you throw some more AH, and the pH should increase, right? With the log of the thing, and it doesn't. It buffers. It stays the same until what time? And at this point, you can no longer control the pH because that's the number of polarized molecules you had. You've run out of polarized molecules because once you've ripped a proton off the water, the OH clings around that and it's used up. So the great thing about this molecule is it's super cheap, it's super durable, and everything is much less volume. And so it's very exciting, and it's the first time where I think this could become commercially viable. Because we're talking about a factor of 20 less energy. And so it's a non-issue. The volume is about a factor of 10 less. So that huge thing becomes a small thing. And moving around incompressible fluid is much easier than moving around gases because work is force times distance, but it's incompressible, so there is no distance. And so it's one of those, you know, all my life I've been lucky. I got lucky again. That's what I count on in my career. Now, there's another way of capturing carbon dioxide that's very effective, given us to by nature. It's called photosynthesis. The amount of crops we plant for food each year is capturing between 10 and 18 billion tons per year, but most of it gets recycled into these things. And so reforestation, that's why growing trees is good, but after 20, 30 years, the forest saturates. And so there's a new material that I propose that could provide negative carbon emissions, not a one-time only. What's the new material? It's called wood. And so structural wood, that is really weird. Structural wood, so people who have a lot of wood, namely Norway and Sweden, have learned to make wooden buildings up to 20 stories tall. In the United States, fire code allows up to 10-story buildings. Fire code means, you know, you think wood, it burns. What the fire department wants is the structure to be standing for at least a half an hour so you can get people out. In a fire, steel buildings collapse because the steel softens. And that's why they spray thermal insulation on steel buildings, okay? Just to keep the building standing long enough to get the people out. So wood is actually as safe. But the question is, how long does wood last? Well, we have some experience with that. Old London has 1,000-year-old buildings. And so I think we should encourage, governments should encourage people to use wood instead of steel and concrete until we can decarbonize steel and concrete. Okay, this has to be wood laminate buildings. There are no more, you don't want to use any old growth forests. And so you have trees that are 20, 30 years old, so you make them out of laminate wood. Okay, now, let me talk about what's really happening. And if you want to talk about sustainability, you have to talk about population growth. And this is the population going back 1 million years, and you see it skyrockets. And the increased economic prosperity of virtually all countries is based on having more young workers to support a smaller aging population. You young people want to be productive so you can support your grandparents and your parents once they retire, right? And so this is known as a Ponzi scheme. For those of you who don't know what a Ponzi scheme is, if you have a lot of new investors who invest, you can pay back the old investors. And as long as you have more and more new investors, you can pay back the old investors. It's a version of economic fraud, but it's happening since economics began, and economists. So now, here's a fact that people all over the world are choosing to have fewer children or no children. And so I advocate that we let the population decline naturally instead of offering tax incentives to have more children. In fact, it's not working among the women. They're not impressed by that. And so if you think historically, again, looking at history, in the transition to mechanized farming, you didn't need as many farmers. And so you have a lot of displaced workers. Yes, people lost their jobs, but a lot of them moved to cities and manufacturing, and they started making cars and washing machines and other things. And so I claim you want to increase the productivity. Increasing productivity means you have to make stuff, but you have fewer people to make the stuff. And so if you have fewer people to make the stuff, maybe you can have robots to make the stuff. And that's the only way you can get rid of this Ponzi scheme or pyramid scheme. Finally, we need a redefinition of wealth. Okay, so a redefinition of wealth. The way wealth is defined today by economists is gross domestic product per person. And how do you increase the gross domestic product? Well, instead of having one car, you have two cars. Instead of having one house, if you're rich, you have two homes. And, oh, by the way, you don't want to keep the car for 25 years. You throw it away and buy a new one after 10 years. And you make everything disposable. So we've turned into a use once, throw it away society. You make buildings that last 50 years, not 500 years. And so you have to change that. And so what do we really care about in our lives? Well, we care about our family and our neighborhoods. We want to be able to send our kids down the block without having an adult accompaniment, and that they won't be sold drugs or mugged. We want to remain healthy and vital and emotionally connected in old age. And so I want to coming near the end, I want to quote Robert Kennedy Sr., who said this in 1968. The gross national product does not allow for the health of our children, the quality of their education, or the joy in their play. It does not include the beauty of our poetry or the strength of our marriages, the intelligence of our public debate, or the integrity of our public officials. It measures neither our wit nor our courage, neither our wisdom nor our learning, neither our compassion nor our devotion to our country. It measures everything, in short, except that which makes life worthwhile. He said this 1 month before he was killed, and very different than his son. So, okay, in conclusion, where are we heading? And how are we going to make this transition from gas? Let's look at history. So in the United States, we transitioned from wood to coal, that's the black. And then you see natural gas and petroleum turning on, that's good. And then you see this little trickle of hydro, nuclear, and other renewables. Say, oh, this is good. It took about 60 years to transition from coal to oil and gas. Maybe another 60 years to transition. Maybe so, maybe not. What's the world really doing? Anytime there's a new source of energy, we just added it to the old source. Because energy does mean wealth, especially if you're a developing country. And so that's what we're doing so far. So we're still on our collision path, 3 degrees, so I'm going to leave you with this image. There's a big boat. It's heading full speed ahead. It looks pretty good. These guys in the crow's nest saying, oh, what's that out there? Nah. Oh, it looks like an iceberg. It's a bloody iceberg. Clang, clang, clang. And then they go on this, in the movie Titanic, there's this dramatic thing of whatever, the engines reverse and everything. And they got poor guys, the young people in the crow's nest, say, turn, why is she bloody turning? Because it takes at least 60 years. Okay, so one last image, one of my favorite images. It's called Earthright, taken from Apollo 8. It was the mission that orbited, the first mission to orbit the moon, followed by Apollo 11. They skipped 9 and 10, and that's how you make progress. You skip some numbers. And anyway, so the astronaut who took this picture, Bill Anders, said, we came all this way to explore the moon. And the most important thing is we discovered the Earth. And so in this picture, there's a bleak moon lunar landscape, no air, no water, not much of anything. There's big Earth, looks very interesting and beautiful, and guess what? There's nowhere else to go, and there is no planet B. Elon Musk talks about going to Mars. Mars has no magnetic field. You get a lethal dose of radiation on Mars. There is no planet B. Okay, thank you.
Okay, thank you, Professor Steven, for your inspiring talk. So to extend our heartfelt gratitude, we now invite Taipei School of Economics and Political Science Student Council President, Elliot Ang, and our TSC students to represent all TSC students in thanking you for today's inspiring lecture. Please stand in the middle. Can we also look at the photographer in the back? Okay. Okay, the front first. Okay, and the back. Okay, thank you. Thanks. Next, I would also like to invite our distinguished guest to take a group photo. Okay, our next session will be a moderated discussion. So before the session starts, we're going to show our QR code on the left-hand side of the screen to submit. You could submit your questions for the later Q&A. And our moderator will be our president, President Gao, and our speaker, Professor Steven, to be in the moderator session.
Okay, what a wonderful talk, Professor Chu. Thank you so much. Definitely a lot more science than I expected, but that's a very good thing because I don't get a lot of science these days. So that was certainly very nice and very multidisciplinary, from material science to politics to cows' intestinal makeup and everything. So I learned quite a bit. So thank you so much. I just want to make sure that we are good on time. Before I start take questions from the audience, I think there's a QR code. So if you want to submit question, please scan the QR code and type in the question. It can be either in English or Chinese. I'll do my best to translate. I think much better than the ChatGPT translation. I think we probably consume gallons and gallons of water and electricity, and definitely room for improvement. So Professor Chu, you mentioned a few things that kind of struck with me, which is the 3 Mile Island incident. And very quickly after that, the public opinion play a very strong part in, at the end, driving up the cost of nuclear energy, as well as the perception of nuclear energy, even to this day. I think this is a very timely topic in Taiwan because the government is currently looking at nuclear energy policy. So my question is, in your experience as a Secretary of Energy, obviously as a scholar and kind of interacted with industry and public officials, the importance of public opinion in driving, say, energy policies, and how does that affect basic science research and commercialization of all the wonderful things that you and other groups are working on in the labs? So if you could comment on that.
Sure. First, the public perception, there are several issues regarding nuclear power. They're worried about an event that could lead to contamination. 3 Mile Island had an accident, but there was essentially no radiation released. And so the best people can estimate in terms of public health, it didn't do it. But it was pretty serious. And because of that, the Nuclear Regulatory Agency, the regulatory agency of the United States, said we have to incorporate more safety measures into the design. Chernobyl and Fukushima were very different, especially Chernobyl. It was a graphite reactor, aerosolized radiation, and thousands, if not tens of thousands of people either died directly or would have died from premature cancers of various kinds. Fukushima, a little bit different, maybe estimated, no one died in the accident per se of radiation exposure, but maybe 200 people will die prematurely from radiation, as opposed to about 20,000 people who drowned. But it doesn't matter. Somehow drowning at 20,000 seems to be much less of a concern than 200. And so what you try to say is, it's not, do you want nuclear or not? It's the choice is, what do you want? And if you want coal and natural gas, then you have to look at the deaths due to air pollution. And that's the relative risk of that. As I said, the spent fuel issue is an issue, but technology, I think, can save that even in places like Taiwan. There's also terrorism and things like that one is concerned about, but you need guards and guns. And so when I was telling at lunch, when our current governor, Gavin Newsom, ran for governor, he was going to shut down. We had two nuclear reactors left in California. He says, I'm going to shut them down. And so a bunch of us convinced him not to, including myself. Because they said, if you want to meet your climate goals, you can't shut down these last 2 reactors. But in the meantime, you can make them much safer. Now, what happened in California, I think, is a prelude to maybe what can happen, both in public sentiment and also in the people in the public sector, public officials, is that you have to be given a choice. And in terms of safety, in terms of everything else, there's no comparison to burning fossil fuel versus nuclear. But you have to make sure. Now, the nuclear power reactors, I was saying, can be even the existing fleet in principle can be made a lot safer. And so what happened was, when 3 Mile Island happened, the United States looked at all their nuclear reactors and they made them safer. These are not tear it down and build a new one. These are little small things that, for example, in California, we have a local water supply. Just in case an earthquake happens, you lose the electricity supply, you lose the water supply, but you have enough water to cool the core of the reactor, and you have enough water to cool the diesel generators that enable you to have electricity on site so you can have control of the plant. In Japan, they didn't do this. Earthquake happens, the water mains got shut off, the diesel generators came on, and they turned off after a couple hours because there's no more cooling water. They should have had a local supply on site, gravity fed, the way we did in California. This doesn't cost a lot of money. I hope they have them now. I hope Korea has them. Taiwan, sorry. I've talked to Japan, Korea, Taiwan. And so I hope all these countries can benefit from the experiences of the United States. Surprisingly, they sometimes don't. And so I think, now, the choice is, if you go to coal and natural gas, first of all, is very expensive, and coal is super polluting, and they're both polluting. And so the other choice is the economy of these countries. And so if you want to be priced out of being competitive, your choice. If you want a safer, cleaner option compared to fossil fuel, it's there. And don't wait for fusion. And so the governor changed his mind, and in fact became a proponent and said, I'm gonna support the relicensing for another 20 years, which the NRC is in the process of doing. And so politicians can change their mind. I met the governor a little while later, and he said, I said, Governor, I'm happy you did that. And he said, yeah, I got a lot of heat for it. He says, you made the right decision. There's also a lot of people trying to take down the hydroelectric dams to restore things to nature. Don't do that. When I was Secretary of Energy, they wanted me to take down the hydroelectric dams in the Pacific Northwest. And I said, I'm not going to do this. You take those down, you're going to burn fossil fuel. And so the politicians need experts to back them and say, this is the right thing to do. And your economy will be better for it as well.
Thank you for that. Wow, there's definitely a lot of questions coming in, and I wish I have a chat GPT right here to help me sort the questions. There is you mentioned in your slide, I'm trying to consolidate some of the questions. I don't go them in order, I try to group them. You mentioned EV. In terms of from the technology angle, energy storage, and also the environment, moving towards carbon neutrality, etc. And the hottest topic these days is how EU is viewing EVs from China. So this is a quite interesting topic because obviously there's a technology front, there's a policy front in terms of EU's 2030 targets and 2050. But at the same time, there's also protectionism at play, also the export control. Duties are being set, and of course, on the other hand, these are democracies and free market economy. So I guess my question is, if you look at just one example like EV in Europe, Chinese EV in Europe, how do we harmonize all these seemingly conflicting principles and special interests?
Yeah, this is a difficult question. I think, again,
we have very smart students and faculty.
I would say that, again, look back at history. What happened is that in solar photovoltaics, it started with very large subsidies from Germany, which doesn't have very good solar. But then all of a sudden it woke up a lot of manufacturers around the world, not only in Europe, but in the United States and especially in China. And what happened was euphoric investment in China went crazy. There was an overabundance of production, and the price of solar just crashed. And as a result of that, the biggest solar company in Germany went bankrupt. A cylinder in the United States, who happened to get a loan from the Department of Energy, went bankrupt. The biggest solar company in China went bankrupt. The difference was in the United States, they attacked me. They gave the loan and the president. And in China, they propped up the company and said, this is temporary, we'll keep you alive until you work out of this hole, okay? And so in the free market economy, it's politics, and so they just blamed the politician. And China had a longer game view. I think the same thing has happened with EVs. First, but the subsidy and the incentive actually came from China. You want to drive a car, internal combustion engine, you might have to wait 2 years, maybe longer. Buy an EV, you can have one now. And they went crazy. The investors went crazy. Lots of overproduction of EVs. I expect more bankruptcy. And so, but right now you have a flooded market. And so then the question is, and then what's going on? Was the government really helping? No, I don't think the government was helping that much. I think it's mostly the euphoric investment that you have to weather. Now, what is happening is before the Chinese cars were inferior, but they're getting better. It's like before the Japanese cars were inferior, but they rapidly got better, and the Koreans, and then the Koreans, and the German cars was always very good. And what did the United States do? They said, we want tariffs. We want to protect us from the German cars, the Japanese cars, and the Korean cars. And finally, tariffs, and they said, or if not, you can make your factory in the United States, so you'll build cars, but the Koreans won't be able to make cars effectively, or the Germans, or the Japanese in the United States. And what do? They came to the United States, they made cars better, lower quality than the American automobile manufacturers. So as a last result, the Americans had to make better cars. I hope we don't have to do a last resort, but now, so it's unavoidable that there are going to be some tariffs politically. But if the tariffs are too high, and I'm afraid they might be easily too high, that protectionism is not going to protect local manufacturing in Europe or elsewhere in the world from superior manufacturing at lower costs. So in the end, don't repeat history. Start trying to make better, cheaper cars now. The tariffs will be there. 20% tariff is, it's been real numbers, maybe okay. Double the tariff, ridiculous, because it's just going to make the local manufacturers, the domestic manufacturers, lazy. There's no incentive. So we do not want to do that. So I would advocate the minimal tariffs that are politically just enough to keep your constituents happy, but too much protectionism is just bad habits. It's like, if your parents are too good to you, it's not good for you. Believe it or not, I know a bunch of really rich, not a bunch, but some really rich people who made the money themselves, and their children are not as motivated by a long shot. And so the protectionism is, we call them helicopter parents. If the kid gets in trouble, the helicopter in, and their extreme version is lawnmower parents. They don't want their children to see any bumps. And so a little bit of, it's up to you to make your life what it's going to be is good.
So now we know Professor Chu is a proponent of tough love. So I think that's
definitely love, but don't spoil your kids too much.
Exactly, don't spoil. Yeah, but it is quite amazing that us as a group, tend to repeat history. We tend to think that somehow we're different, and we're going to do it right this time, and fail to take lessons from our past. I think what you just described from Korean cars, Japanese cars, German cars. Just an example, I think the future, we need to learn those lessons and do it right.
I know, I'm one of those people who study history and condemned to watch history repeat itself with those who don't study history.
Yeah, so students, remember, history is good for you. It actually helps us figure out how to move forward by not making the mistakes that the other has made before. So there's many questions on my list on the Taiwan situation in terms of nuclear energy. As a former Secretary of Energy, what kind of advice will you give to the Taiwanese government in terms of their energy policies? You know, obviously, Taiwan government has also committed to net zero by 2030. It has gone through a period where nuclear energy is really not viewed favorably, both in public opinion as well as in actual implementations. But there might be some changes in the air, I'm not sure. But what kind of advice will you give?
I think I applaud the government's and the people's decision to embrace mitigating climate change and to decrease carbon emissions. Very, very important. You don't do this by burning coal or natural gas. As I said, capturing most of the carbon dioxide from natural gas doesn't really solve the problem. It solves 3/4 of the problem. And you still have the deaths from air pollution. And think about the economic prosperity. Energy does matter. The cost of energy does feed directly into the cost of manufacturing goods and the cost of life in general. And so if you have a clean source of energy where you have solutions for the spent fuel problem, where you can make the current reactors safer if not done already, but the new generation reactors, when I was Secretary of Energy, I was saying for the small modular reactors, the minimum design you lose complete control of the reactor, the electrical supply, the water cooling, and you can't do anything. That they'd be walk-away safe. They would never melt down. And that is a requirement. That was a requirement in 2009, and it is embedded into our system of these small modular reactors. They're walk-away safe. The large reactors, you want to be at least have enough heat inertia so you don't get a serious meltdown. So you need 3 years of enough thermal inertia. The smaller ones, we already have that technology. And so you have economic prosperity and less carbon pollution and less particulate matter, air pollution on the one hand, and you have something that's safe. So I think despite the history, and maybe in the early history in Korea, there was stuff done about nuclear waste issues that were not good. That's history, okay? You just don't do it again. Everything be transparent and be very open and sharing with the public. But the other thing is, it is much safer and it's less dangerous. And it's important for your future prosperity.
Thank you. Thank you for the advice. I guess my next question, and also reading the submitted question, is NTHU is the only university in Taiwan with a nuclear science college, and it's really one of the founding academic units on this campus. So we've been developing talents in nuclear science and for energy and other uses, including medical, for many decades. You should go visit our reactor. It's quite interesting. So what is the role of universities, NTHU or Stanford and any other university, in terms of getting ready, both in terms of the university as an energy consumer perspective, as well as universities as training platforms for students, either consumer of energy or the innovator of renewable energies. What should universities do in terms of working with the society at large to achieve this net zero?
Well, you're an education and research entity, and both are very important. Let me describe something that happened 3 or 4 years ago at Stanford, maybe 5, I don't forget when. We had an open discussion, hundreds of people attended. We had a group that was against nuclear and a group that was for nuclear. And it was a debate. So there were experts who were against nuclear, and there were experts for nuclear, and it was open, and people could listen and then ask questions afterward. And that's the most important thing. Don't try to hide things. Don't try to do in some back room. You know, get it out in the open. What are the issues against it? And what are the issues for? And just discuss it. So the most important thing is to sponsor these public dialogue events. Not to say, oh, this doesn't matter, and we'll try to do some secret way of doing one way, or either killing it or making it come back. And so use the main advantages of a university of open intellectual debate to get these issues. The other thing, of course, is to realize what are the issues, what is at stake. And you can't just ask a narrow question, do you want this? It's what are your choices? Right? There are choices. You can't say, I don't like this. And okay, so if there are people in the United States who are against, you name it, anything. You'll find them. and so
Same thing here, though.
same everywhere in the world. And so yes, it's a democracy, and so in a democracy, if you have your main advantage is to try to create a new generation of people that can take in data, try to evaluate it, try to listen thoughtfully to both sides, and try to be part of that debate, rather than having some secret society or cabal or this or that to decide what is done. And so I think that's very important. So we do this at Stanford. There's a debate as to whether Stanford should have a nuclear department. We don't have a nuclear department.
Oh, we can play together. You can.
You know, and you know
We can consider a collaboration on that front.
Well, the things, no, there's like 3 or 4 or 5. MIT has a very strong nuclear department. Texas has very strong nuclear department. Purdue, Berkeley, Wisconsin, and so they said, no, that's enough. You don't need. It's not like a physics department where you have to have a physics department. Physics is the root of everything. All good. But you don't maybe need that many nuclear departments. You just need good nuclear departments, and you need the other universities to be participants in this discussion.
Well, I'm very glad one of the things that you get to do is to talk to our deans of nuclear science after this. So I look forward to more collaborations coming out of this. And thank you for reminding us the unique roles of universities is really about open communication, open dialogue, of sharing of different ideas. I think that with the mutual respect. Easy said than done. I think Taiwan is a very young democracy, 30, 40 years, and US is a democracy in transition. And for universities to maintain that academic freedom and mutual respect is an effort that I think we need to really work hard at and really champion that. And of course, it takes the effort of all the students and faculty to make it happen. Thanks for reminding us of that. Yeah, it's very important. Well, we're almost coming to the end of the Q&A session. So let me read off arguably the most popular question that most people have asked in my little tablet here. It's about the new administration in the US. There's a lot of people out there curious about how the new administration will view net zero, will view international cooperation, achieving a joint target for the humankind, and all the challenges that will come along the way. So do you care to comment on the, I don't want to do it by force. I mean, not that this will be done by force, but it is the most popular questions from the audience.
Well, I don't blame you. It is the most popular question in the United States as to what to expect. And, you know, in truth, there's a lot of people very worried. One doesn't really know what's going to happen until it happens. The first term could be a prelude. It could be better or it could be worse, depending on your political point of view and many other things. But let's start with something that's important to you, and that's international relationships. And again, I'm going to give you a history lesson. I've got 6 minutes. History is good. And so, so the history lesson is what happened after World War I and what happened after World War II. After World War I, the French and the British were victorious over the Germans. And so what did they do? They punished their enemy. And they did a lot of other stupid things in the Middle East, and the Ottoman Empire, the Turkish Empire, the Ottoman Empire collapsed, and politicians started drawing lines willy-nilly without any understanding of any historical context, without really understanding everything, but they were victors and they started drawing stuff. And so they laid the seeds to the failure of Germany, a huge country failure that let an Adolf Hitler come to power. They laid the seeds to Middle East unrest that we're still seeing today. And it was just tragic. Then what happens? World War II. The United States, with the Allies, but it's really the United States that was the victor. And what happened is something happened in history that really didn't happen before or since. The total unconditional surrender to the United States. And the United States, instead of punishing their enemy, they rebuilt their enemies. Germany and Japan. They invested billions to rebuild their society, their structure, the order, that ended up being a formula for a half a century or more of peace. Incredible. You know, never happened before. And it was a wonderful thing. And so I think you have to remember, if you do something, and you know, the Marshall Plan, all these other things, it was an amazing thing. And the United States also did something. They said, we will be the security, the international security in Europe and in Asia. Okay? We will protect against foreign aggression if it's, you know, uncalled for. And so out of this, you know, NATO, all these alliances were formed, and it was the nuclear might and the military might and the steadfastness of the United States that said, we're not, we would have little wars, but not world wars. Now, my biggest fear is that the United States withdraws. It pulls away from NATO. It pulls away from any Pacific alliances. And it said, that's none of our business. And in the end, it is our business, because the stability of the world will affect the United States as it will affect the entire world. And so that is my biggest fear. I don't know, will there be enough wise people in the United States and enough inertia to say, no, 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 no. An isolation policy would be very destructive to the world order and stability, okay? This is not a conquering nation that said, you're listening to us. Now, and I have to say candidly, the United States in the recent past has become a bit of a bully on financial matters. The dollar is controlling everything, and the financial bullying of the United States is not healthy, right? And so the United States actually has to go back and study a little more history of how to behave for a while the only world power after the Soviet Union fell. And so I think we can improve a lot, but I think the international stability is very important. And before the election, something rarely ever, I think it never occurred, that retired national security authorities, this is mostly like high-ranking generals in the armed forces, they're retired. The current ones don't, we have a commander-in-chief, they have to stay out of politics. But the retired ones were very alarmed by this isolationist policy. And actually, they asked me to sign it because, I was a former Secretary of Energy. I was, just in case you knew, you have to be really nice to me because we control the nukes. That's true. Every letter, I have to sign a letter with the Secretary of Defense to the President of the United States, assuring that the arsenal, the nuclear arsenal, was safe, secure, reliable. Safe meaning it doesn't accidentally go kaboom. Secure means if a terrorist gets hold of us, they can never make them explode. But if you want to make them explode, you can make them explode. Every year, a personal letter has to be signed, and I spent 3 days reviewing what we do in the Department of Energy because we're the stewards of our nuclear arsenal. So anyway, so that's something of concern. The tariffs, I hope, things get moderated and they don't have super high tariffs. It's good populist things, but it's going to be very inflationary. It's going to be a lot of things. So that I'm concerned about. In terms of energy policy, environmental protection, I think the previous administration, they said they were against it. The funding agency I started, RPE, the President Trump, former President Trump, the first term, asked to zero out the budget. It was like $250 million a year and zero. And the Republican Congress actually increased the budget because they said, no, this is one of the best parts of the Department of Energy around. We're going to increase it. So there is some inertia. And so I don't know about things like that. The current secretary nominee designated, or he has to be approved, said that 5 degrees climate change, not a big deal. Maybe we get worried if it's 8 degrees. Just remind you, just in case you don't know about history, the ice ages was 5 degrees colder than we are today. Canada and the United States down to Pennsylvania, Ohio, covered year-round in glacier. Only 5 degrees. So 5 degrees warmer, an equally different world. Okay, so I don't know, that person, you're not going to change the mind of that person, for sure.
There is no plan B, right? Yeah.
But I don't know. I hope things work out, and we can hope for the best, and try. He is the president of the United States, and so this is the way it is. We live in a democracy. He got a majority of the votes, but there are other issues, and I'm hoping the inertia and the stability of the United States will carry us through, and maybe miracles will happen and Trump turns out to be a wise president.
At least we will have a recording of today's event, and we'll send the White House a copy, and then maybe he'll take time and study it. Yeah.
Anyway, so let's hope for the best and see what happens. No matter what, he is the president of the United States, and other countries have to work with the U.S.
True. I have a very strong feeling that Professor Chu is just like me, a student of history, and I'll spend 1 minute and share with you the origin of NTHU. We were actually formed in the late Qing Dynasty with the war reparation money to the U.S. Congress, and the money was set as an endowment by an act of US Congress to set up the academy and to train the best students and send them to the United States. So as you said, that in the past there has been a time where the US government really was trying to do things for the betterment of everybody. And actually NTHU is the result of that. So I think we all maintain some level of optimism, for the U.S. going forward. And I think what we can learn from history is that it's better to work together and then trying to cut each other's throat.
So another little anecdote regarding this, for those of you, how many of the young people know the Boxer Rebellion, what started it? Raise your hands.
As in Qing Dynasty.
Okay. Okay, so
Well, not too many.
Not
I'm
too many. So
surprised.
this is
wow. We need to strengthen our history,
Okay, so what happened?
general education.
What happened way back when in the 1800s
义和团，义和团就是 Boxer Rebellion。义
is
和团应该大家都 OK 吧？
Great Britain was taking opium from Afghanistan and places like that, and they were shipping it to China with the deliberate intent of turning the country into drug-addicted people. They did not ship the opium to Great Britain. So it was drug dealing, government sanctioned, government supported, government done. When I told my mother I was dating a British woman, her reaction was, British, bad people, bad people.
Your mother is an NTHU alum, right?
Well, it's from Tsinghua in
Beijing.
Beijing. So, but during the war where they went to Kunming, so during World War II, 4 universities went to Kunming, West China, and same year classmate was Yang Xinyin. So he was a family friend. Anyway, so she said, bad people, and then she met her, and then she liked her better, and she liked me, so. So what happened was then the Chinese rebelled. There's a Boxer Revolution. And they said, this is terrible, we're becoming opium addicted, we have to rebel against this, we have to stop this. The British are ruining the entire country, and the rebellion was really put down with full force. And the Brits wanted to punish China, so a huge fine, reparations. And the United States somehow got some of these reparations, I don't know why, but you know what the United States did with them? They gave them back to China.
Yeah.
That's what you're talking about.
That's the beginning of the Tsinghua Academy. Yeah.
Whereas the British took the money. In fact, the British wanted the money for the loss of sales. It was
a choice. It's a choice they made. but
Yeah.
I'm glad the U.S. made a different
so
choice.
that's why my mother was really anti-British. It goes way back.
On that note, what an exciting past 2 hours. We heard everything from physics to policies, a bit of history. Let's join me in thanking Professor Chu one last time.
We would like to once express our gratitude to our distinguished speaker, Professor Steven and President Gao, for sharing their invaluable insights. So before we end the event today, I would like to, we could return to the seat. Oh yeah, you want to take a photo? No,
Okay, let's thank Dr. Chu again.
Okay, thank you. Thanks. Could we also take a group photo with everybody so we could return to the seat? And then we'll have our photographer to take a photo on the stage.
Okay, 1, 3, 2, 1。好，来，大家看我这边喽，来，1、2、3。